Okay, welcome back. Kids are now safely on the trampoline, so hopefully I will not be disturbed again. Right, question 2, very similar to question 1. You need to work out the order of the, to deduce the order of the reaction with respect to A and with respect to B, and use that to work out the overall rate expression. So this, obviously, rate equals K times the concentration of your reactants, A and B, and then we just need to work out whether it's going to be raised to anything or not. So we can work out the order with respect to A fairly straightforwardly using experiments 1 and 2, because for experiments 1 and 2, the concentration of B is the same. So we can see fairly easily, so this is for A, 0.36 divided by 0.12 equals 3, and if we look at what happens to the rate as this is increased by 3, we can say, so rate equals 1.89 times 10 to the minus 3 divided by 2.10 times 10 to the minus 4, and that equals 9. So 3 squared equals 9. Therefore, with respect to A, it is second order. So I'm just going to put a 2 that Molly, what you doing, darling? Right, you can't talk, okay? Good girl. Right, so I'm just going to pop a 2 there. Now we need to find the order with respect to B. Now, just as in question 1, we don't have any concentrations of A here that are the same that we can use to calculate B in a straightforward way. So what we're going to do is use experiments, where are we? Let's use experiments 2 and 3. Okay, 2 and 3, and we can see, so this is for B, we can see that for experiments 2 and 3, the concentration halves. Okay, so I'm just going to put here experiments 2 and 3, the conc times 0.5. Okay, now we've already worked out that the order with respect to A is second order. So we now need to look and see what happens from here to here for experiment A. So, is it boring, Molly? Yeah. 0.72 divided by 0.36 equals 2. So that's times 2. Okay. So we're going to follow the same method as we did for question 1, and we're using experiments 2 and 3. So we're now going to say, that was times 9. So from here to here, we're going to need to work out. So we're going to say 1.89 times 10 to the minus 3 times 2 to the power of 2. And that is going to give you 7.56 times 10 to the minus 3. And then final step, so I'm just going to put kind of to indicate some stages here. Final stage, I'm going to say 3.78 times 10 to the minus 3 divided by the number we just worked out, 7.56 times 10 to the minus 3 equals 0.5. Therefore, as the concentration halves, the rate halves, this takes into account, this calculation takes into account that A is a second order. It's the reaction is second order with respect to A. This calculation takes that into account. Therefore, with respect to B, it's first order. I'm going to put B first order, and so we don't need anything there. Okay, so that's your rate expression. I think that's all we need to do for that one. Yep, and that's 3 marks. Okay. Question B. Can you still see that? Yeah. Okay, question B. Use the data from experiment 4 to calculate the value for the rate constant K at this temperature. So we've been given the rate equation, so we know the order of C and the order of D. Lovely. 3 marks. One of those is going to come from the units. 1 mark is going to come from rearranging to get K, and 1 mark is going to come from the correct answer. So K equals rate over C squared over D squared. Now it is worth writing the expression like this in the rearranged form before you enter any numbers. The reason being that if you just had a bit of a cock up and actually used the wrong, you know, you're looking kind of in a rush, and actually what I would do probably is just highlight that, so that you don't accidentally use that number or something like that. But if you did do that, then writing it down like this, if this question were worth more marks than this, probably would potentially pick you up a mark. So we're then just going to plug in numbers and make sure that we times that one or square that one, and then that one, and that will give you, sorry, just referring to, calculate this earlier, 56.98 or 57.0. You then need to calculate the units. So the units for rate, and you're actually given them here in the table, so that's nice. But we're going to have that over that, and we can therefore cancel that and that, and that. We're left with that and that, so we're going to say 1 over that to give us mole to the minus 2, just put the number in there, dm plus 6, and then s to the minus 1. Calculate a value for the initial rate experiment in 5. So we've calculated K, and so therefore we're in a position to calculate rate for 5. They've given you this question here broken down into sections. You could just get that question and it might be worth 4 marks, and you would need to recognise the steps that precede this final bit. But this is only 1 mark. They've given you the units. So rate equals K was 57 multiplied by 1 minute, darling. Multiplied by 3.6 times 10 to the minus 2 squared times 5.4 times 10 to the minus 2, which gives you 3.99 times 10 to the minus 3. Okay.
Could I do some work?
Some work? Yeah, go and get one of your sheets it's on the stairs. Right. Next question says explain qualitatively, so I'm not going to do it, if that's okay with you. Right. The last question of question 2, question E, I am going to take you through. Can you still see that? Yeah. However, this relates to the Arrhenius equation, and you're not doing that yet. That will be next week's work, but I will do this now. It might be that you want to pause this video here and come back to it, but essentially you don't really need any knowledge of the Arrhenius equation in order to do this. All you need is some basic mathematical understanding. So as I say, when you do Arrhenius, you will come to know this, but our temperature is already in the right unit, so that's fine. And we've been given this equation, which is the version of the Arrhenius equation that you will become more familiar with. And you're being asked to calculate a value in kilojoules per mole for the activation energy of this reaction. So activation energy is that. Okay, now there are different ways of doing this. The way I'm going to calculate it is the way that I would do it if I were answering a question on this, where you have to use a graph. Please stop. Thank you. Where you have to plot a graph and then you work out the gradient, and the gradient is equal to that. And so once you've got the gradient, you just multiply that value by this, and that gives you EA. So I'm going to kind of do it in the same way as that. So we can say minus EA divided by RT equals ln K minus ln A. So first thing we're going to need to do, I'm just going to put this in bullet points. One is we need to work out ln k. Well, we have, in fact, no, right. Now, when I did this earlier, I got this wrong and I couldn't work out why. And the reason being, because I was skim reading things, I used the wrong k. I used the k that we had just calculated in the previous question, which was 57. You are given a value of k here of 6.51 times 10 to the minus 3, and therefore that's what you need to use. So that should give you minus 5.03. And then you're given the value of your gas constants A and R, and you always will be. So we just need to, we've got A, we need ln A, so ln A equals ln times 2.57 times 10 to the power of 10, which equals 23.97. Okay, so now...
That's very good, Mummy.
Oh gee, thanks. Thank you, James. Yeah, Molly's doing, I'm so sorry you're 12. Molly's doing so well. Go and get some off the stairs. Go and get some sheets off the stairs, okay?
Okay.
Right. Goodness, where was I? Dumps. Right, so now we say that equals minus 5.03. Take away 23.97. And you then are going to multiply. So this equals this, okay? And we just want this. So therefore, EA equals this, which, have I written that answer down? Yeah, minus 29 times RT, which is minus 29 times R is 8.31, temperature is 300, and that gives you 72297. Now, it's really important, and I will be banging on about this a lot when we do Arrhenius. The most common mistake here is to not divide by 1,000. You are being asked for an answer in kilojoules per mole, and you have been working in joules per Kelvin per mole. So you need to divide this answer by 1,000, and that is going to give you 72.3. Now, the last thing I say about this is that you're in a position here to do a bit of a common sense check, and activation energy for any reaction will nearly always fall within the region of 40 to 4,000 kilojoules per mole. And if it doesn't, which that doesn't, then you know you've gone wrong somewhere, and where you've gone wrong is probably you failed to divide by 1,000. Okay, so lastly, question 3, A and B. Now, in the interest of speed, I'm not, you guys need to be super quiet, okay? Be super, super quiet. You're being so good. In the interest of speed, I am, good boy. I'm not going to draw that tangent because I've forgotten my ruler. I've got some answers here. So you can see here that this is what the tangent should look like. Okay, so it says to draw a tangent to the curve when the constant... Yeah, I'm being noisy because I'm making a video, mate. Yeah? Good boy. Draw a tangent to the curve when the concentration of butadiene is 0.0120. Okay? So we're going to draw it there, and it must go through 0. Okay? And basically it should look like that. Okay? And we're going to use these figures for part B. So part B says the initial rate of reaction in this experiment has this value. Use this value together with a rate obtained from your tangent to justify that the order of the reaction is 2 with respect to butadiene. Okay? Shh. Please, my darlings, I don't want to start this video again. So, the tangent is obviously going to be the change in concentration over the change in time, and that's what a rate of reaction is. It's concentration over time, change in concentration over time. So part A, I'm going to kind of do this in 3 steps. Part A is to calculate the gradient. Okay, so you're going to say, where are we? So it's 0 if your tangent's drawn correctly, and it might be slightly different, but I'm just going to use the values that we've got here. So the rate, the concentration at 0 is 0.16, so it's 0.016 minus 0, and here it crosses at 7,800. So calculation of gradient is going to be, what do we say, 0.016 minus 0 divided by divided by 7800 minus 0, and that gives you 2.05 times 10 to the minus 6. Okay, right. So step 2, or B, is we need to work out the change in the rate. Okay, so how the rate changes and how the concentration changes. Just like, I'll go back, just like here, okay, so we work out how the concentration changes, and when that concentration changes, what that does to the rate, okay? So we're using the graph in the exact same way. So, rate changes, we had initially 4.57 times 10 to the minus 6. The other thing actually just to say here is, again, I'm a big fan of doing common sense checks. The rate that you calculate, the gradient that you calculate should not be wildly dissimilar to this. And if it is, and if it was 10 to the minus 5 or 10 to the minus 7, that's probably fine. But if it's massively different, possibly you've gone wrong there, okay? So we're going to say 4.57 times 10 to the minus 6 divided by the rate that we calculated. So this is the new rate, times 10 to the minus 6, and that gives you 2.23 rounded. We're then going to work out the concentration at the start. So when the rate was this initially, the concentration was this. So I'll put here rate conc. So 0.018 divided by what the concentration is when this was the rate, okay, which was 0.012. And that gives you 1.5. All right, so our concentration has changed by a factor of 1.5. If this reaction is indeed second order, then we would expect the rate to have increased by 1.5 squared. Now 1.5 squared equals 2.25, and that is sufficiently similar that we can confirm, yes, this order is this reaction is second order with respect to butadiene. I am so sorry for the background noise. Okay, bye.